Right, hello, we're now listing prime numbers and expressing numbers as a product of their prime numbers. This is section 1.8, the foundation course, page 27. This very quickly becomes grade C. After one or two questions I'm into grade C. So what do we got then? We know such things as factors exists. These are little numbers that squeeze into bigger numbers. For example, the factors of 6 are 1, 2, 3 and 6 because 1, 2, 3 and 6 fit into 6 exactly and leave no remainder. But a prime factor, in other words, factors which are prime numbers also exist. So for example, if I look at 6 as an example, I've got 1, 2, 3 and 6. These are the actual factors of 6, but 2 is a prime number because it has no factors itself apart from 1 and 2. That's the only way to make 2, 1 times 2, and 3. The only way to make 3 is to go 1 times 3. Therefore, 2 and 3 are prime factors. Is that alright? Let me just write it. Okay, so 2 and 3 are prime factors. They're numbers that go into 6, they're factors, and they also happen to be prime numbers because they have no factors apart from the number themselves and the 1. So let me have a look at these. Let's just list a few prime numbers. It's good to learn these because when you come to use these later on, you won't be thinking, is this prime or isn't it? Right, the smallest prime number on the earth is 2, then it's 3, then it's 5. The only way to make 5 is 1 times 5. Then it's 7. Not 9 because you can make 3 times 3 to make 9. Next one's 11. Next one, 13. Not 15 because 3 5s, not just 1 times 15. 16, 17. 18, 19, 20, 21, no, 3 7s are 21, 22, 23, yeah, etc. You won't normally need to go further than that in order to work with prime numbers, but that's a useful list to learn. Certainly at least go up to about 13, and then after that work it out yourself. Let's have a look. I'm going to go straight into question 4 actually. It says write each number as a product of prime factors. Now, let me go to another page. Products of prime factors. So it says 24. Now, if you take 24 as the number, you can split it off loads of ways. If I go 2 and 12, well, 2 is a prime number, so I've sort of arrived there. That can't be split any further. And let's go back to my splitting. Well, 12, I can call it 2 lots of 6. The 2's finished. Let me just round that one off, or rather put a ring round it. I can go further with my 6. I can call that 2 times 3. Again, I'm multiplying. That's what I'm doing. And 2 and 3 are both prime numbers, and therefore prime factors of 24. So what have I got then? I've got 2 times 2 times 2 times 3 should make 24. So let's take a look. 2 2's are 4, times 2 is 8, and 3 8's 24. So that's completely correct. If I want to write it in index notation or power form, I've got 2 to the power of 3, look, 1, 2, 3, multiplied by, that's what it says there, 3, and that will make 24, as you know. Now, that was not the only way to split up 24. I can go 6 times 4 if I want to, or 4 times 6. No prime numbers there. Split up 4 into 2 times 2. There's no other way of doing that one. So here I go. I've got a 2 there and a 2 there. And I've got my 6. Only one way of splitting the 6. 2 multiplied by 3. They're both prime numbers, as you know. I'll just close them off. And there is again 2 to the power of 3. 1, 2, 3. Multiplied by 3. Again makes 24. So you don't have to go down the prime number route each single time. But you can use this wonderful little tree method. Call it factor tree if you want to. Why not call it something? So it's a prime factor tree. Put the word prime there as well. Only ever do this with prime factors. So there we go. It's a prime factor tree. Oops, went over it. Never mind. No, prime factor tree. Split it off how you like. You get down to prime numbers, then express it in index form. Now let me show you the method I really like to use, and that's going on this page now. Now look, let's start with 24. We're doing lots of little short division sums. We're saying what's the smallest prime number on earth? That's how I teach it in class. Well, 2, sir. Alright, fine. Does 2 go into 24? Yeah. 12 times. So it's a bit like an upside down short division sum. Have we finished? No, we have not. Does 2 go into 12? Yes, it does. 2 goes into 12 6 times. Try again. Does 2 go into 6? Yes, it does. It goes 3 times. Does 2 go into 3 exactly? It does not, because 2 is not a factor of 3. What's the next prime number therefore? Well, the next prime number is 3, and 3 goes into himself once. What have I got? 2, 2, 2, 3. So I've got 2 times 2 times 2 times 3 makes 24, just like on the previous page. Writing it in index form, we've got 2 to the power of 3 multiplied by 3 is 24. Okay, I think I'll do another one. Let's try a dodgy one. Write each number as a product of prime factors and use index notation. Better write that up here actually. Index notation. Let's just put that into normal English. In other words, powers. Yeah, put it into little powers, alright? Okay, so index powers. So index notation, or write it as powers. I've now got a horrific one, 144. So I could use this the tree method, or I could use the this little division method bit by bit. Oh, here we go. Right, 2 does go into 4 because that's 144 because it's even. That's 72. Even number. 2 goes in as a prime number. That's going to be 35 plus extra 1, 36. 2's into 36. Well, that's 18. 2's into 18. That's 9. Uh-oh, odd number. Does 3 go into 9 as the next prime number? Yes, she does. 3 goes into 9 3 times. Just crossed Catherine's Chapel there. 3 goes into 3 once, and I've landed it. So let's just write the answer over here. I've got 2 times 2 times 2 times 2 times 3 times 3. Let's just write that carefully in index power form, index notation. 2 to the power of 4 multiplied by 3 to the power of 2 gives us 144. Please note, according to our rules, we cannot add the 4 and the 2 to get something to the power of 6. We don't have any number multiplied by itself 6 times over, so please note you can't artificially add that 4, that little 2 and create maybe 23 to the power of 6 or 6 to the power of 6. Doesn't make sense. You know it won't make sense for the simple reason that, look over here, there's your 4 2's multiplying together, and there's your 2 3's. Alright, just be absolutely sure. 2 to the power of 4 is there, 3 to the power of 2 is there, and here we are multiplying them to get 144. Alright, any more like that? I want to do question 8 because it's taking this a little further. It says, page 27 still, write each number as a product of prime factors using index notation. Alright, so I'm going to do it for a reason, and I'll illustrate the power of what this can do. So I've got to do 27, let's go back to black, I've got to do 27, and I've got to do 45. I'll do them separately. First express them as a product of its prime factors using powers. So here I go. 2 doesn't go into that, 3 does. 3 goes in 9 times, 3 goes into 9 3 times, and 3 goes into himself once. So I've got 3 to the power of 3, oops, is 27. Do the same to 45. 2 doesn't go into that, but 3 does. 15 times. 3 goes into 15 5 times, and the next prime number after 3 is 5, which goes into 5 once. So I've got 3 to the power of 2 multiplied by 5. That will make 45. Now that bit you know. It then says use your answers, those up there, to find the highest common factor of 27 and 45. So highest common factor, or otherwise known as HCF. Here we go. What have they got in common? They've got 3 to the power of 2, well so does 45, and 27 has 3 to the power of 2. Look, 1 there, 2 there, and he's got 2 as well. So we're looking at 3 times 3. Do they have anything else in common? No, they do not. Therefore, the highest common factor will be a 3 from each, 2 3's from each rather, and that will give us 9. Okay, so basically the 3 squared is 9. Alright, that's the highest common factor. Now let's do the lowest common multiple. This is a little bit more tricky. So let me write it out again. The lowest common multiple. In other words, LCM, or least common multiple. Now here we take each base number, each factor, we take the highest power. So here 3 to the power of 3 beats 3 to the power of 2. So I definitely want 3 to the power of 3, and that takes care of that one. And certainly if 3 to the power of 3 is the highest factor for 3, then certainly 3 to the power of 2 will go into it nicely. Now what's left? We have 3 to the power of 3 is nothing else. We have a 5 on its own. We have to include the 5, otherwise 45 won't go into the number we're trying to find. Essentially what we're doing is finding the number into which 27 and 45 will go. So let's work it out. 3 to the power of 3 is 27. Then we must multiply that by 5. I think I'll do a little sum on the side here. So 27 multiplied by 5. 5 sevens, 35. 5 twos is 10. Plus add on the 3. 13. Answer 135. So it would seem then that the least common multiple, or the lowest common multiple, of 27 and 45 is 135. Now let's just work out some little extras here. 27 plus another 27 gives us what so far? 40, that's 54, isn't it? Add on another little 27, we're just building up the story bit by bit. That will give us 70, 81. Add on another 27, I hope this fits. That gives me 108. Oh dear, I've got this in the way. Never mind, let's start down here. 108, add on another 27. That's going to take me to, that's a 5, carry it over. Yep, I've landed 135. So really I've added lots of little 27s and I got there in the end. And so I've got 135. We'll do the same with a 45. So start with 2 45s. Where are we? 90. Add another 45 after that, and we'll gradually build up the picture. So 45 is there, add it up. What have we got then? Actually I don't need that 45 dangling in the way. Get rid of that. What do we got then? So 5 plus nothing is 5. 9 plus 4 is 13. 135. Even doing it the long way shows that both 45 and 27 meet up again in the future, and the future is called 135.